Hi, let's talk about the Lab 12 soluble and insoluble salts. Typically in the class we don't do the last two sections. They're kind of fun to talk about, but experimentally they just don't work very well. All right, so the first part, you're mixing together two dilute solutions and doing a double replacement reaction. So in the very first one, for example, you're taking silver nitrate, aqueous, plus aqueous sodium chloride, and you've got this soup of ions that now can recombine if various factors dictate that. So the possibilities are if we take silver nitrate and sodium chloride, we could get silver chloride and sodium nitrate. So what we're doing is mixing them and we're observing what happens. In this particular case, we would see the formation of a precipitate. People just write PPT for precipitate, and then we have to figure out what it is. So in this lab, the rule that we go by is any of the group 1 cations, so that'd be lithium, sodium, potassium, and the ammonium ion, are always soluble. So if our choices are that we either formed silver chloride or sodium nitrate, we can cross out the sodium nitrate because it would be soluble. It would not form a precipitate. So from that, we'd say, oh, well, the formula here, since we have a +1 and a -1 for our product, must be AgCl. All right, and then we do the same thing for each of these. So we mix silver nitrate, the sodium sulfate, and we see what happens. I guess we should write down what the ions are here, so go ahead and do that. In this case, nothing's going to happen. The silver nitrate, sodium phosphate, we see a yellow precipitate. The barium nitrate, sodium sulfate, we see a white precipitate. Calcium chloride, sodium hydroxide, we're not supposed to see anything, but sometimes there's a little confusion from carbon dioxide forming carbonate in the solution, but officially nothing happens there. Calcium chloride, sodium sulfate, that's an iffy one. We'll say nothing happened on that one. And then calcium chloride plus sodium carbonate definitely forms a precipitate there. So then your job is to go through and write down what all the ions are. This should be easy for you. The one caution is don't look at this Na3PO4 and say that you have an Na3 3+ or something. It's definitely sodium ions and phosphate ions, not Na3 or Na2 or whatever else it might be. And then from these guys, you're going to write formulas for the solids that were formed, so just in those places that we have question marks. And again, that should be a quick review from some of the nomenclature stuff. As far as an answer to this question, solid precipitates form because the ions are more strongly attracted to each other than they are to the solvent molecules. And we talked about that on the board in class, maybe in our last meeting there. All right, so again, good review in a couple of ways: naming simple compounds, recognizing that these polyatomics are entities unto themselves and not just a sulfur and 4 oxygens, but rather that is a sulfate, etc., etc. All right, the second part of the lab is the one that really takes a little more time. And what we do here is the students take a small sample of potassium nitrate and try to dissolve it in 5 mils of water. Potassium nitrate is very soluble in water, so even though you only have 5 mils and you might have 5 grams of potassium nitrate, oftentimes that can dissolve. The thing about it is it's temperature sensitive. So what we do here, and here's some data that the winter class did just this year, is that some students are given 2 grams of potassium nitrate and they dissolve that in the 5 mils of water. They heat up the water. As they cool the water down, they see at what temperature crystals start to form. So from this data, we see that 2 grams of potassium nitrate. In the second part of the lab, we're taking potassium nitrate, which is a very soluble salt, and seeing what the solubility is in water as a function of temperature. So you're taking a relatively small amount of the potassium nitrate, we weigh it out for you, 2, 3, 4, 5, 6 grams, and adding it to 5 mils of water, and then we're going to eventually convert that to a solubility, which is defined as grams of solute in 100 mils of water. So all of these masses get multiplied by 20 to go from 5 to 100 mils of water, and that's actually what gets plotted as the y-axis. All right, we happen to have data for this one from this past winter's lab class, and so a couple of students were given 2 grams. They recorded the temperatures where the solubility was reached. The way this is actually done is the water is warmed up, and then as it cools off and crystals start to form, just as we hit that saturation temperature, those temperatures are recorded. So again, at 2 grams of potassium nitrate, we're seeing these kind of high 20s temperature. When we go to 3 grams, that takes a temperature of 37, 38 degrees. If we'd had 3 grams of potassium nitrate and we were at 27 degrees, 2 grams of the potassium nitrate would have dissolved and 1 gram would have been just left as a crystalline solid in the container. So your task then is to go through and plot these temperatures, and it's sort of backwards. Your temperature is your abscissa or your x-axis, and your solubility, which is this mass potassium nitrate multiplied by 20, is going to be your what we think of as the dependent variable, even though we're doing the experiment kind of backwards on that. All right, so to put this in practice then, what you want to do is on your report sheet, copy these numbers down, and I'll just leave them at the end of the video, into the temperatures. So again, these guys can all get squeezed into temperature, and the solubility, the 40, 60, 80, etc., are going to be these guys here. When we plot, the solubility is your up and down axis, and the temperatures are going to be the x-axis. So just like it shows on the sheet. Okay, let's just do a couple of these real quick and dirty. They don't have to be perfect, but you know, give it an honest effort of graphing. So I'd say, all right, at a solubility of 40 grams, there's my 40, I'm going to have temperatures of 24, 25, 26, 27, 27, 29. So I want to come down here and say these guys are 5-degree intervals. So this is all going to be really, really close. You know, I'm going to have 24, 25, 26, 27, 28, something like that. Then when I go to the 60s, my 60s are going to be there. That's out at the temperature in the high 30s. So let's see, this would be 30, 35. So this is 40 right here. So I'm going to have a string of points kind of in there. So go ahead and make them points, make them little X's. Don't just, you know, pencil prick, put them down. But they're going to be close together, and there's not a huge gain in being exactly in the right place. All right, once all this is said and done, you know, we got our points wherever they are. Then what we want to do is show that there's a trend there, and we typically do that by throwing a curve through it. Don't connect the dots. There's no real reason to even have a straight line here, but whatever the data kind of shows, you're going to see some sort of a curve that represents that. This solubility information is shown in the textbook in chapter 9. There's a chart on one side of the page. Maybe I'll go look it up later. In any case, if you just look up solubility, and you can see what it should look like for a whole bunch of different salts. Some salts are very temperature dependent. Potassium nitrate is, you know, it goes up rapidly as we look at the temp and the solubility. And other ones are much flatter. Sodium chloride, for example, has a relatively minor temperature dependence on its solubility. All right, so describe what you see down here. And then the last little bit, the last page, we should answer these couple of questions. And so with these questions, try to do is the roadmap. So we have a conversion factor here of 320 grams of sucrose per 100 grams of water. And a roadmap might be asking grams of water, 2 grams of sugar. I'll just put S for sucrose or sugar. And so I'm going to have my 200 grams of water, and I'm multiplying that by 320 grams of sucrose per 100 grams of water. And I've run out of space, but clearly that'll be 640 grams of sugar. The important thing here is I've made this conversion factor that lets the units cancel out. And then lastly, kind of a logic question. I'll let you muddle with that. So end it there, and that's what you're going to turn in. And as promised, here's the data if you just want to park on that to copy it down on your data sheet. Count to 5 and turn it off.